Hi, today I'm going to show you how to use the ID21 base workflow to do PCA on your XANES dataset. The first information you need is that you can download Orange via this website, orangedatamining.com, and it's a free download here. Once you've downloaded Orange, when you will open the OWS file that will be saved on your process data folder, Orange will most likely ask you to download the spectroscopy add-on that you will need to that we use in our workflow. If it does not ask you immediately, you can download it using the option add-on just here. The first thing you need to know when you want to use this workflow is that Orange requires the data to be shaped in a very special way. This way is the following. So here you can see an Excel spreadsheet, and you want basically that each scan has an individual name to have each scan, each spectrum being as a row. So here you can see on the first row, we have here the energy scale, and then we have a first spectrum, a second one, a third one, etc. So to retrieve this data shaped like this, the ID21 team prepared a script that you will have here in this isolated widget called XANES extract. This script will be set up by the help of your local contact. And when you are on the experiment, the only thing you will have to do is run it in order to overwrite the previous data table that was generated. It will generate the data table that you want with the name inputted here and save them in the directory that you specify here. Once you have run it, to open this file, you just have to use the file widget here that we called data. If the file was already open, you can reload and you overwrote it because you acquired new spectra. You can just hit the reload button here. Else, you can browse through your directory to find the file that you want. So this is the file that I want to open. This one has been automatically generated by the script that I showed you, but I did a minor modification. So when you use the script, you will have automatically your spectra put in a row, the first row being the energy scale, and you will have three columns. A column that is named scan, where you have the list of the name of the scan given by the query. Each scan is has an individual name, where you have the sample name, the point number, and the action number here. Then in the column sample tag, you will have the name of the sample as it was declared in the query. And finally, you will have a column that is usually called sub-sample tag, and this is the tag that you manually input via the query when you input the tag on the point. Here, because I will work on a reference data set, I modified manually this file to change the name subsample tag by mode and say if I recorded the data in transmission or in fluorescence. But in your usual query generated file, you will have here subsample tag and the tag inputted for every point. When you open the file widget, you will have this window opening. So as I already told you, reload if you just overwrote the file to have more XANES data, and here to browse through the directory of your computer. And you will have every individual column listed here. Automatically, the scan name, the column scan, will be detected as a text and be qualified as a metadata. All the energies that you have here will be identified as numeric data, and will have a feature role. The feature role are the things that you want to compare together. So in your case, you want to compare the spectra. So indeed, all the energy points has to be declared as features. And finally, the sample tag and usual subsample tag, and in this case, mode, will be declared as categorical because there is no number. It's a string that is inside the cell, but they will be wrongly automatically declared by orange as feature. So in order to properly declare them, because they are metadata, you can click here on the role and select metadata. Once you've done your change, you can just apply the change to the rest of the workflow. For information, you can add as many metadata columns as you want. So if you have other information that you want to add, don't hesitate to open the CSV file by Excel and manually add new columns of metadata. For instance, the provenance of the sample, if you have additional information about the dead time, etc. The second widget that you will see at several points on in this workflow is the data table widget. This one is has a very practical use. It's just a display of the table that you are working with. So if you have any doubt at any moment during the workflow, if you see that something is not working correctly, don't hesitate to add a new data table by just linking it after the widget where you think there is a bug, and to check what is your data table, what are the data you are working with. The next two widgets here are widgets that allows you to manage your metadata. The first select column is just to be sure that all the energies are indeed well declared as features and all the metadata are well declared as meta. Sometimes when you reload your file at the beginning of the workflow here, sample tag and subsample tag will be, although declared as metadata here, they will hit the feature here. So don't forget to have a look there to move them back in metadata. And if it's the case, you will notice very quickly because it will just make your energy scale very weird from 0 to 500, because here I have 500 features instead of the real energy scale here. The next widget, select row, is the one you are very interested with. So this widget allows you to add conditions on the metadata that you want, the type of spectra that you want to select and process together according to your metadata. So here, for instance, if I want to select only a few samples from my list of samples, I can ask to have in sample tag the condition that it's one. For instance, here I selected the KBR salt, egg white, egg yolk, and maybe I can add egg yolk with PBO and sanidine, for instance. You can add several conditions together. So if I want, for instance, to only see the spectra that were acquired in fluorescence, I can say mode is fluorescence. And then all the spectra that will be sent to the rest of the workflow will be the one that answer both of these conditions. So this is really an and not an or. So the sample will be part of this sample list. So I will remove the biotite hollandite and phlogopite spectra, and I will only keep the spectra that have been recorded in fluorescence in this case. Then the workflow is branching out. The two bottom branches here allow you to have a look at your XANES spectra. The first one here, XAS normalization, is a typical XAS normalization. So it's actually a pre-processed spectra widget from the spectroscopy add-on, where you have several different preprocessors. And in this case, we ask for a XAS normalization, and you have to declare the position of your edge, the position of your pre-edge before the edge to do the normalization, and the position of your post-edge, once again, to do the normalization. And then what will be shown here in the norm the widget that we call norm XANES, but which is a spectrum widget, is just display the XANE spectra. So here you can see their display, where you have as a bold line the average spectra of all the spectra that are, so in this case, you are averaging by sample tag, so with the sample, and you will see in a lighter color the dispersion of these spectra. Sometimes having the dispersion is a bit hard to read, so the line that is just above allows you to average the spectra, for instance, here according to their sample tag. We have exactly the same normalization, and if you hit the norm XANES, this time you will see only the average without the dispersion, which can be a little bit more readable. The most interesting branch of this workflow, and the one you will most likely work with, is the top one here. To implement PCA, we at ID21 like to work on the second derivative of the spectra that will calculate using a Zawadzki-Golay filter with these parameters, because it allows to highlight even more the small differences that you can have in the shape of the spectrum. Then we use a vector normalization to prevent the concentration artifacts that we can have. And if you are only interested to do your PCA in the part of the spectra that is varying a lot, you can add a cut keep widget and select really only the area where you have most of the variation, so that the noisier area do not give any artifacts on your PCA, or as low artifact as possible, let's say. If your spectra are very noisy, in some cases, it might not be a good idea to derivate your spectra, because it might increase even more the noise. So in case of very noisy data sets, you want to replace this, the Zawadzki-Golay filter and the normalized spectra, by a typical ZAS normalization. The next step is the PCA. The PCA is implemented automatically, and you can see here the variance explanation, so the curve of the PCA. So the first principal component here, in the case of the dataset that we selected, explains already something like 67% of the variance. Then the second one is a bit below 20%. The third one is at 4.8%, etc., etc. Depending on how you want to process your PCA, you can either ask, okay, I want to explain 95% of my variance, and it will tell you how many components you need to explain such amount of the variance. Or you can say, I want only this number of components. So if you think 2 is enough because you would just use this to have a grasp of the clustering aspects, you can say, I want 2 components, and it's telling you that it's explaining 86% of the variance. What you want to do generally is to select only the principal components that explain a lot of your variance, because a component that explains only 1% of your variance generally is just focusing on the noise and is not very significant. So here, typically, we can work easily with 3 components. If you want to have an idea about the shape of your component, you can click here on component and ask not to have any average. And you will see here the spectra of the pseudo spectra, the 3 components, what they do look like. So you have here component 3. If you leave your mouse on the curve a little, like 2 seconds, it will show you which component it is. So here you have component 2, and here you have component 1. But the most interesting part for you will be the scatter plots, which is the display of your different sample points. So here you see the display of sample 1 versus sample 2. Everything is gray, which is not super interesting. So you might want to color the points according to the sample they belong to. So here you can see that I have my potassium bromide reference on one corner of the PCA plot. It's clustering well together. You can have my sanidine, you can see my sanidine points are also clustering together over here. And here you can see my egg, my different egg samples that are clustering also together at another corner. And you can see in red the egg white, which is separated from the egg yolk in green and the egg yolk mixed with minium in orange that are all clustering together. You can zoom on this curve using the scroll. You can pan this curve by clicking on the hand here and move around. If you want to zoom to a specific area, you can also just zoom by drag and dropping the area you are interested in and selecting the magnifying glass. And if you want to come back to the shape of the scale that displays all your points, you can hit the reset zoom button. So PCA is a very interesting tool to cluster your points, but in some cases, you want to see if the difference is actually real. So to do this, you'll have to go back to the spectra. And to see the spectra, you can actually, if you select the mouse here, select an amount of spectra, and they will be here highlighted in orange. If you want to add additional spectra to the group, you can hit the control button and select other points, and you will see that they will be highlighted once again in orange. If you want to create another selection group to compare, for instance, two average spectra on the group, you can hit the Shift button of your keyboard and select the new spectra here, and your two groups will be highlighted, one in blue, one in red. Selecting the spectra will actually feed the rest of the workflow that is usually not fed, and allows you, so here basically we are retrieving the spectral information, averaging the spectra according to group, which is basically your selection, doing a normalization again, and then you can have a look at your spectra. So here you have the spectrum widget. The color of the spectra in this window is the same as the color of the spectra in your selection. So here, my blue spectrum is the points that are surrounded in blue, so in my case, egg white, and my red spectrum are both egg yolks that are mixed together. When you are selecting, this is live updating, so if I hit Shift and select the sanidine, for instance, here, you will see the sanidine appear in green like here. And once again, for the KBR here, you will see the KBR appear in orange. If I deselect everything by just selecting a white area, you will see that the spectra disappear because I'm not selecting any spectra. It's always very important, once again, to have a look at the spectra if you see a trend, because PCA is a mathematical treatment, which means that it does not know anything about physics or chemistry. Sometimes a trend can be noise, can be self-absorption, or an artifact. So looking at your spectra across a trend is very important to understand if this trend has physico-chemical relevance or if it's just an artifact. Once you are happy with your selection, so typically, let's say that we are happy with these two groups. If you want to further process them using software like Athena, PyPhi, or Larch, you might want to save the spectra. So you can save the raw spectra here. They are already transposed so that your table, your spectra are in column and not in line as Orange requires, so that you can open them directly with your usual folder. If you want to save the already normalized spectra, because here we are saving raw average and not normalized average, don't hesitate to just here add a transpose and a save data widget to save the normalized XANES spectra. Finally, in some cases, you want to use this typical workflow to implement statistical analysis, but you want to compare your data with some references. To do this, you will have to change a little bit the opening here. And instead of having just a file, so you can break this link here, you will have your data. You will have another file that has been created here that will be your references. And to compare them using PCA, they need to have exactly the same energy scale. So to do this, you want to have the references being interpolated to the energy scale of your data. Be sure that your data and reference energy calibration is the same when you do this operation. So the data point is the energy scale to which the data will be interpolated. And then once you've done the interpolation, you can do a concatenate to merge both tables and add them in your typical workflow. So this will help you compare several data sets. And if you have even more, you can break this link and add another data set with another interpolation and concatenate them together, etc., until your whole data set can be compared together. I hope this tutorial has can help you to process your data using the typical ID21 based workflow. As you can see, Orange has several other options to compare your data. For instance, k-means if you want to do other types of clustering than PCA. So don't hesitate to explore the software a little bit and to ask any help to your ID21 local contact. Thank you very much and have a nice day.